So hey guys, Abelu here, IBM Storage. We are starting our encore session. Some requests about having a deep dive conversation on HyperSwap. So here we are for session number 9 of IBM Systems Back to School. Today I will be the most quiet guy in the room, so all the speech and discussion, although I have a question because this topic is very interesting to me, and I have some questions from BPs that I couldn't attend, so I will make these questions later. But I was here and I disappear in the stage, Mr. Barry the Wild Duck White. Up to you, Barry.
So I'll make sure I leave some time for questions at the end. I suspect there might be a few as we go through here. So, welcome everybody to this final session in the series. Several people had asked if we could cover HyperSwap, and so here we are. HyperSwap is obviously one of our features that is actually involved with duplication of data. So normally we've been talking about data reduction and trying to save copies of data or save from making copies of data, but really when we're talking about disaster recovery and high availability, we're actually wanting to duplicate the data to make sure that we have it. So typically, obviously dedupe and things like that is going on inside snapshots and backups and all of those kind of things. But when you're talking about keeping a business running, and if the worst possibly does happen, then you want to make sure that you have another full copy somewhere, and it needs to be a full copy of the data. Obviously, if you completely lose one of your data centers for some reason, through some natural disaster or through some kind of physical reason, then you need to have another copy of it somewhere. So given that you're having to make another copy of your data for that what kind of data reuse could you maybe get out of that other copy of data, and how easy is it to actually set up something like this? So before we kind of delve into the kind of nitty-gritty on HyperSwap, it's worth taking a slight step backwards and looking at, well, what are the various options that we have for disaster recovery? Because hopefully you're not going to be in a position where you're like Dilbert there, where you're running around like a headless chicken if something does go wrong. So you want to have a tried and tested plan as much as anything else. And it's all very well putting a DR or an HA solution in, but you want to make sure that it's been tested properly to ensure that when something unexpected does happen, you know what the procedures are, how you're going to go about bringing up another copy of the data and regain access to your data and production. So just quickly going over the different options, then we'll talk about two different things really here. And there is the standard kind of disaster recovery techniques, and then there's high availability techniques. So disaster recovery is really about the ability to resume after some kind of disaster. And that can be done at different levels. Obviously, it can be the entire site, or even just one component within an infrastructure that is actually being recovered from. DR does sort of require generally a specific failover task. So at the point of the disaster has happened, there's a specific set of steps and procedures that you have to follow to bring up the other copy of the data. And to that end, there's usually two different metrics associated with all of these. One of them is your recovery point objective, and the other one is a recovery time objective. So the first one, the RPO, is how much data have we actually lost? So if you have a point in time copy of data, then it would be obviously anything that has happened since that point in time that you've actually lost. And so different types of disaster recovery can have different RPOs associated with them. Ideally, obviously, in the best of all situations, having an RPO of 0 means you've lost no data, and then having a recovery time of 0 would also mean that you're not actually having to do some kind of failover So basically, in a DR situation, usually the recovery time is greater than 0, and depending on the type of DR being used, the RPO or the recovery point may be greater than 0 as well. Where high availability differs is that you have generally continuous access to the data during and after a specific disaster. So effectively, you have an RPO and an RTO 0. But depending on how you set up even a highly available situation, you may still have some recovery time involved. You shouldn't be losing data, but you may well have to do some processing, some human interaction or human intervention to actually bring up that other copy of the data. So, again, before we go into some of the kind of deeper dive stuff, let's just remind ourselves of some of the terminology that we're going to use here. And this is specific to the kind of Spectrum virtualized set of products from IBM, the Flash system, the old Storewise systems, and obviously the SVC system as well. So we talk about nodes. So all of these systems are clustered systems of some form. And even if you just buy a single unit, then it is a cluster. And so a cluster is made up of these nodes, and a node would be a single processing unit used essentially to build pairs, or IO groups as we call them, and we'll cover that in a second, and then create clusters from. So with SVC, it's fairly simple. It's a single SVC engine, so a single SVC piece of hardware is a node. And you need multiple nodes to obviously build a usable system. With a Flash system, the whole system is usable, but it's made up of 2 nodes. So when you buy a single Flash system, in the back of it are 2 canisters, and those canisters themselves are individual nodes. And so when we go into an IO group, as I said, in order to build up a usable kind of redundant pair, we have this IO group concept. And so with SVC, that's 2 nodes to make up an IO group. And with Flash system, the IO group is always the 2 nodes inside the single enclosure itself. So with SVC, if you're setting up an SVC system, you have to add the nodes to the cluster. So you start with 1 node, and then you would add another one in, and you tell it the IO group that they're going to be added to. With a Flash system, all of that's taken care of for you, and so the system will automatically create a single IO group out of that pair of nodes inside the enclosure. So then moving on to a cluster, you can then take those IO groups and put those together to create larger systems for sharing of storage, for providing a single management interface, and providing additional performance capabilities. So the 2 examples in the pictures here, we've got the first one, which is a 6-node SVC cluster. So that's 3 IO groups that have been clustered together. And then with the Flash system, that we're showing an 8-node 4 IO group system. So it's 4 enclosures, and they've all been clustered together. And usually the clustering is always done over the fiber channel. There are situations where you can do it over Ethernet. If you're using ISAR and things like that, you can cluster them together over Ethernet. But traditionally, or generally, most people will always use the fiber channel to actually create these clusters. So they all communicate over a specific set of ports so that they can see each other and they know the other working set, the other members of the cluster itself. So that's kind of basic terminology. So we've got the nodes, the IO groups, which is the pairs, and then the cluster. When we're talking about disaster recovery, particularly, we create an additional thing, which is a partnership. Now, a partnership is defined at the cluster level. So we're creating partnerships between 2 distinct clusters. And so the idea is that you would have a production site with a cluster running of it at it, and then a DR site where the other cluster is running. Now, they don't have to be the same products or the same size or the same capability. So one of the nice things with these all running the same functional code, the virtualized code in them, is that you can size things based on the workload that's going on. So at the production site, maybe you have an SVC system with a bunch of storage behind it, and then at the DR site, you might just have an individual flash system or a Storewise or any of the other products. So it doesn't have to be exactly the same. But that partnership then is defined to say, okay, I'm going to send some of my data to another cluster in terms of kind of particularly the DR type relationships. So the MetroMirror and the GlobalMirror. Usually you would only have two systems in a partnership. You can have a single kind of source system or a single target system and have multiple clusters partnered into it. But at any given point, a volume is usually only in a relationship that is between one partnership. The caveat on this, and I haven't covered too much of that in this, is the new 3-site configurations that we're supporting as of earlier this year. And there is some links to some red papers talking about those at the end. So just closing off on the disaster recovery capabilities then. So MetroMirror, this is our synchronous replication. So I mentioned about the RPO, the recovery point, being a time-based thing as to how much data potentially you would lose in the event of a site failover. So with MetroMirror, with it being a synchronous copy of data, the RPO here is 0. The RTO is going to be however long it takes you to actually kind of trigger. And in this slide here, we're talking about the various steps, assuming that something has gone wrong. So with this, all writes are mirrored. They use that partnership. You have a source volume at the primary site, and then you have a target volume at the secondary site, and they are designated as a master and auxiliary. And so the master is the source and the auxiliary is the target. And the reason that we differentiate those between the primary and the secondary site is that the relationship can switch direction. So at any given point, we're always copying master to auxiliary, but you can switch the direction and switch the role that the volume has. And the reason you want to do that is after the recovery, after a failure. So generally in a synchronous replication situation, the impact here is to your primary workload in terms of latency. So whatever the latency is between the two sites, every write will see that round trip latency added onto it. So synchronous mirroring, therefore, write at the primary site, copy it to the secondary site acknowledges that it has a copy of it, and then we will complete back up to the host. So you're always guaranteed that when the server and the application has acknowledgement that the write has been completed, that you have it in both places. It's copied to both sites. Obviously, you're only ever accessing one site at a time. So in this case, the primary site is running the workload, the source. And during that time, when the replication is active, the secondary site is in a kind of read-only mode. So you can mount it, you can read it, you can access the data there if you want to, but you cannot send any writes to it. So everything comes through the primary site. If there's an actual failure at the primary site, then obviously the replication stops. And at that point, you can mount the volume at the secondary site as read-write, restart your applications at that secondary site, and resume. And that's your RTO, that's your recovery time. So however long it takes you to do that operation of starting the application again and then resuming business, that's your RTO. Obviously, once you've then fixed whatever happened, hopefully it's just been a temporary thing at the primary site and it's not truly been wiped away for some reason, then you'll presumably want to revert back and run everything back at your primary site. So once you've recovered it, you can then flip the direction of that copy, synchronize everything back from the secondary site, which is going to be the most up-to-date, and then obviously flip back again so that you're copying in the same direction. So that's a standard synchronous replication situation. The other version or main version that we support is what we call GlobalMirror. So this is an asynchronous copy. This by implication means that your RPO is greater than 0. So this time the writes come into the source and we acknowledge back to the host that we've accepted that write before we've confirmed that it's copied to the secondary site. So the asynchronous nature of this means that the writes are sent to the secondary site asynchronously to the completion of the host IO. So by doing that, it means we can have longer distances between the primary and the secondary site. I think we support up to 8,000 kilometers if you really want to go that far, but obviously there is a finite amount of buffering that can be done because we've got to buffer those writes, send them to the secondary and acknowledge them back. So if you truly have enough incoming write data that you can actually saturate those buffers, then it starts to actually flow back that latency potentially onto your primary writes. So the main difference here, all the rest of the processing is the same kind of failover, failback type operations, but it is only crash consistent at the secondary. So because there's a potential of lost data, we guarantee that it's consistent, but it's consistent as if there was a crash of the application. So it will always be up to date and usable, but there might be some journaling and some replay of operations or transactions that needs to happen to bring that secondary site back up and running. So we also introduced a third type of DR, really for when either you don't have enough link bandwidth to saturate or to cope with that buffering that I mentioned about. And this is GlobalMirror with change volumes. And the idea here is that we will periodically take a snapshot, and that snapshot is obviously crash consistent at that point that the snapshot is taken. And then we will synchronize all of the changes since the last time we took that snapshot. So it's in a cycling mode. So say every 5 minutes a snapshot's taken. It means at most you will be 10 minutes behind at the secondary site. And at the secondary site, we take other snapshots to guarantee that we always have one of these crash consistent copies available at that secondary site. So it's a way of utilizing a much lower bandwidth link, divorcing away the amount of change that's happening from the link bandwidth that you have. And this is traditionally used with IP-based replication rather than channel-based replication, particularly if you're running on 100 megabit type connections or even 1 gigabit connections. Those kind of links obviously can't sustain very high throughput, and so this is a solution that can provide you that. So before we go on, Abilio, I'm going to pull you in there and see if there's been any questions or anything, since I can't see the chat about any of that before I move on to the true HA things. If Abilio's still there, of course, he's on mute. He's not.
G'day, Barry. It's Andrew.
Andrew, you made it.
How are you? I'll save him. Yeah. So the two. One was a comment is that you could lose data in an HA scenario if there's data corruption in the database and you have to resort to the last backup, which is true. But that's not the type of disaster where we're talking more of a site outage or a component failure. So Darryl rightly points that up, and you would need to restore back or to a snapshot. And then there was a question with regarding the old IP replication chestnut. With 4 partnerships, can we have multiple IP replication? And Seneca and I have both answered that, saying you can only still have one IP relationship, or one cluster can only be in one partnership by IP. Just got a new one. GlobalMirror with change volumes needs additional capacity for snapshots. What's the rule of thumb to size the additional capacity?
Yeah, no, that's a good point. So obviously they would be thin provision snapshots. And so the rule of thumb is really around what's your change rate. So for example, if you set your cycling period at 24 hours, and in a 24-hour period you wrote the entire capacity that you're replicating, then you would need 100% additional capacity, or in fact twice as much capacity, because you've got 2 change volumes at each site. So the reality for most people are around about a 25% additional capacity is a reasonable rule of thumb, but obviously there's going to be kind of outliers where you have very high rates of change. So it's really how much data is changing between each of your cycle period, and typically we see maybe 5–10% change.
Excellent, thank you. That's good. That was from Deepak. And that's it for the questions so far.
Cool. Right. So let's go on to some of the HA solutions. So the first HA solution that we have is stretch cluster, and I'm going to cover this very briefly because obviously we talked about HyperSwap as the main thing, but this was a precursor really to the HyperSwap functionality. It was actually coined, the name and the phrase was coined by a business partner, and so really it's actually a stretched IO group if you think about it. So this is an SVC only functionality. It requires the kind of independent nature of the nodes that are available inside an SVC system. And so in a normal SVC situation, we have a pair of nodes, single IO group, we have a storage pool, and we have a volume presented up to the servers. The volume is mapped to the hosts, and each of the nodes is providing paths to that volume. So one node will be designated the preferred node, and that will be giving us preferred paths to that volume. The other node is the non-preferred node, and it's providing active paths that can be used, but they have this designation of non-preferred, and so that's shown there with the blue and the white arrows. So that's a standard single site type configuration. So what we can do is we can actually stretch that IO group to create what's called a stretch cluster. Now we still have exactly the same config. I'll just go back because we only have one volume. It's just that we have multiple paths to the volume. So when we stretch it, what we actually have is still one volume. We create two copies of the data. So there's an inbuilt functionality inside Virtualize called volume mirroring. And this is not to be confused with all of these replication mirroring technologies we're talking about. This is more like a logical volume mirror, where inside the system it can have two storage pools, and one single host volume gets two copies made of it. So what the servers see as a single volume, we're creating in two different storage pools, and we're just cloning everything across those two storage pools. So if you set it up in such a way that that volume is using this mirroring functionality, and those two storage pools are in two independent sites, and you stretch the two nodes between those two sites, then you can actually create this stretch cluster configuration. So we still have paths at both sites through both nodes down to the storage, and then the system itself is keeping the data mirrored between these two storage pools. So in the next picture, it's a bit clearer. So we've still got that preferred and non-preferred nature. And so when you create the volume, you designate which node you wish to be the preferred node for that particular volume. And in this case, we've said, okay, the node that is in site 1 is the preferred node for this volume. And so when a host in site 1 is accessing the volume, it will say, okay, I'm in site 1, the node here in site 1 as well, therefore I'm going to access this node because it's the local one, and so it stops it from having to go across the long distance link to the other node. At the same time, the other node obviously still presents its non-preferred paths, and so we still see paths to the other site. But because of this preference, the system will generally always use the blue paths rather than the white ones. So we can set it up in this way, in such a way, and actually change the way that we report this preferred nature depending on what site you define for the objects. So in this case, when you have a stretch cluster, you define the site for the storage, you define the site for the nodes, and you define the site for the hosts. So whenever it all matches, so when a site 1 host sees a path to a site 1 node, it's reported as preferred. But in the case of the white path, when it's site 1 host, site 2 node, it's seen as a non-preferred path. So we don't have to have any special software running on the host. It's all just handled by standard multipathing. The server honors the multipathing rules. And so by the very nature of this, it keeps the traffic where it can within a site as opposed to having traversed the inter-site link. So as I said, if you have a volume, that same volume, and it's being accessed through applications on site 2, it will see a different reporting of paths just because of this site awareness. And that is the main difference between you, if you've seen when we talk about stretch cluster and enhanced stretch cluster. So it's the only difference is that enhanced stretch cluster has this site awareness built into it. And so if you set it up in such a way that you define all the sites, then you get this enhanced nature. So why would you use stretch cluster? Well, stretch cluster utilizes that volume mirroring functionality. It's not making use of any of the DR capabilities in the product. And so you could combine this with DR as well. So you can have this local HA functionality and then add in on top of that to have the Metro GlobalMirror, the change volume type behavior to create 3, 4, or even now 5 sites, all with a copy of the same data. So obviously very excessive, very paranoid people if you want to go that far, but in theory you could build a 5-site configuration using 2 stretch clusters and then having replication between those and then another replication coming off of that for your 3rd site with a snapshot based onto the 5th site. It's only SVC. Obviously it requires the IO group to be split between the 2 sites, so the flash system can't provide that. One of the things though that it does mean is that if we go back to the previous picture, say you do lose site 1, then obviously you've lost that node. And so those 2 nodes are doing the write caching. And so at the point that you lose that node, you're down to only having a single node providing the access for those volumes. And so we switch into a write through mode at that point. So at that point, you'd ask, is there a better way? Well, that's exactly why HyperSwap was created. So HyperSwap, the picture looks very similar, but here you'll notice the subtle difference is that I'm not using SVC here, I'm using flash system boxes. And so you have a cluster of flash system. So this is a 2 IO group system. So you have a flash system at site A and a flash system at site B. And then the rest of it looks the same, only we're not using that volume mirroring capability. We're using a special version of the MetroMirror type functionality, an active version of MetroMirror. So similarly to before, there is actually only one volume. So that volume that you see up at the top with the yellow lines going to it, that is the single volume that perceptually the hosts see. So it's one volume with a single unique identifier, and then both of the sites can see that volume. Behind the scenes, actually, there are 2 volumes. So the 2 white volumes, one at each site. It's just that they're presented at each site as an identical volume. So this, by its very nature, has site awareness built into it. And so you have all that same benefit that we just talked about. But technically, there are 2 identical volumes. One when you're accessing things through site 1, and one when you're accessing things through site 2. And then this special version of MetroMirror keeps the 2 in sync. And so it's slightly different from the way that the stretch cluster truly is just a single volume, and it's pathing that's different. Here, there are actually logically 1 volume, physically 2 volumes. So main difference here, we now have preferred paths being presented by both nodes in this IO group. And so instead of it just being 1 node on the left-hand side when we had the stretch cluster, you have obviously the 2 nodes that are in the back of this enclosure, and both of those nodes are presenting preferred paths whenever it's being accessed through the same site. So here you define the site for the IO group, define the site for the hosts, and so whenever the sites match, they will stay and they will present those preferred paths. Similarly, you see preferred paths to the other IO group, so the other flash system, and they will be seen as non-preferred paths. So you have the same kind of redundancy and capability in that if for some reason your fabric goes down at site 1, but you still have access at to the fabric at site 2, then it will fail over and use those non-preferred paths, even if it's just a fabric issue, for example. So all of that means that in a kind of normal running situation, we have essentially I/O going to a particular node, or a particular pair of nodes. So that we've just gone in to look at the back of the node there, or the back of the two nodes, and so paths are presented up from both of these. You've got some I/O running. It's going to be running there, coming in from site 1, moving down, sending into the node, and then something happens. That node fails. We have a single node failure occur. So automatically the system will just say, well, I've got more paths, more preferred paths, in fact, and so I can just carry on running. And so with a single node failing, you're not actually having to cross over and use the other site. In this case, we've still got another node in the local site, and so it will continue to use that. So it sees all of those paths as preferred paths, and it will just carry on staying within the same site. So that's the single node scenario. If we have a storage loss at one site, so in this case we're seeing all the same paths we normally do, and this time we lose the storage system itself. Well, that takes away all of those preferred paths, but if our servers are still up and available at site 1, then at that point we're going to use those non-preferred paths. And we still have caching, we still have all the redundancy, because we still have 2 nodes in the other site that are providing the access. And so it means you can suffer single node failures, double node failures, or entire site failures, depending on how you set things up, and we'll cover that in a minute. So hopefully that's fairly clear. So in that scenario, we've still got the redundancy, we've still got the 2 nodes servicing I/O. However, your latency may well suffer. Obviously, you're crossing that link now. Your application is on site 1, your storage is on site 2, and so we're having to actually traverse that link every time to do I/O. So I mentioned about depending on how you've set it up. There are 2 main kind of ways and use cases for actually deploying these 2 different modes. And so the most common way really of setting this up is not truly using it in a highly available way. It's using it in the storage as HA, but your entire infrastructure isn't HA. So here we refer to this as an active passive mode. So in this situation, you've set it up all as we described. Your application, however, is kind of single-sited. So your application, in this case something running on Red Hat, is running on site 1. So that application runs there, is accessing all of the storage. But if site 1 completely fails, so that whole thing goes up in flames, obviously we still got access to the other site. However, your application was running at site 1. Because you were running it in this active passive mode, your application wasn't site aware, your application wasn't clustered, you have to actually restart the application. So although you potentially don't have any loss of data, you're back to having a recovery time objective in this mode. How long does it take you to restart the applications and activate them and get them running again at the second site? So it takes the storage away from the problem of having to be highly available. It's always there, it's always in sync. It's been a committed piece of operation to the storage, then you're guaranteed that that is there at that second site. So most commonly used, as I say, because it's relatively simple, it doesn't put any requirements onto the application side or the operating system side to have its own clustering and so on. But it does provide more of a DR-like solution. Still requires that failover at the application level, but at least the storage is all there. But it is highly fault tolerant. You've got no data loss for any committed writes, but the applications may have lost some uncommitted operations. So if they were in the middle of processing something at the point that it failed, that hadn't actually made it to the storage yet, then there might be some consistency checks that need to be run to reestablish and bring that application up. So that's the first use case, this active passive mode. The second use case is truly an active-active situation. So here you're running a clustered application. And so you're running both at site 1 and at site 2. You might have some kind of workload optimizer that's sending it to make use of all of both sites. And this is actually a really useful way of running. But it may be that in the previous situation, you can get some reuse of your hardware because you can offset and have some of it running at site 1 and some applications running at site 2. And then that way you're actually getting use of the compute power that you have at site 2. I mentioned about what can I do? I've got to make 2 copies of this data, but how can I actually make better use and get some value out of having that second copy? So that's one way of doing it. Do a bit of balancing act, half of it at site 1, half at site 2. Here you're letting the application clustering take care of all of that for you. You don't have to worry about it. And it is truly active in that if the application or if site 1 fails, everything just carries on because your application is already running, it's already active, it's lost some of its nodes, some of the clustering piece may have to take over at the server side and move some of the workloads or restart them, but it's all handled by the application at that clustering level. So this gives you a true active type solution. So it does require HA-aware application unlocking, and that means that you have to have some kind of quorum or some kind of locking mechanism built in either at the operating system level or at the application level. So kind of rack clustering, for example, with Oracle and those kind of solutions. Does mean there is no failover. It's truly what we mean by this HyperSwap concept of it's just always on, it should be extremely fault tolerant. We've got no worries even about crash consistency because everything's always just being updated all the time. No human intervention is needed at the point of a site failure. Nobody in theory should even notice if a whole site has actually gone down. And it allows you to obviously load balance the more dynamically or let the applications do that load balancing of both the storage and the servers at both sites. So I mentioned about Quorum. This is a critical piece to running any of these kind of clustered type technologies. So in a clustered system, there is a Quorum device, and so there even in just a standalone flash system, there's Quorum devices. It's all less obvious to you because you don't need to worry about it so much. But in a HyperSwap system, you have to have Quorum, and the use of it is more prevalent due to intersite link failures. So the point of Quorum is to act as a tie break in the event of a kind of split brain scenario, as we call it. So if you have half of a cluster at one site and half at another site, and you lose the link in between them, then you have 2 independent halves. You don't want both of those halves continuing to run because you're going to get out inconsistent data. So you need to pick one of them to actually run, and that's the act of, or the job of this Quorum device. And so in the scenario where you lose the link, both sites are still up. Both of them will actually try and communicate with the Quorum device. They will say, okay, I'm still here. And so at that point, there's basically a race that happens to get in and lock the Quorum device. So the Quorum race begins, the Quorum device sees, okay, I've heard from both of them, and then it will make a decision to say which of the sites is allowed to carry on. During the point where this Quorum race is happening and this Quorum decision, all I/O is halted. So you don't want any I/O to continue until someone has been told to continue and someone has been told to stop. And so this all happens very quickly to enable this Quorum failover, or this Quorum race to be won. So various things about the Quorum devices. You want the Quorum device to be hosted at a 3rd site, ideally. Now, most people maybe don't have 3 sites. This can be problematic, but it could be somewhere on your standard IP network domain. It could be just where your people are actually working as opposed to the data center itself. But it's up to you to define exactly how independent you want that 3rd site to be. It could be a different hall inside a data center. It could be a different power domain or different racks. But you just need to understand the concept that this thing has to be up and running at the point that you need this quorum to be used. So in the event of one of your sites failing or the link failing, you need to make sure that the connectivity is there to this quorum device. So it can be a fiber channel attached thing. Okay, it could be another storage controller. So the quorum device can be defined as a storage device attached to a third data center, a costly option, but if that's the way you want to do it, you can do it that way. More commonly, people use the IP quorum application. So the IP quorum app is basically generated by the system. So you run a command on the system when you're in one of these stretch topologies, it will generate the application. It's a little Java app. You post that on a virtual machine somewhere, and it needs to have IP connectivity to the service IP address of each node. So as well as having a management IP of the whole cluster, every node in the cluster has its own service IP, and it's that mechanism it uses for communicating with them. So consider what will happen to your IP network under failure scenarios. If your gateway is at one of the sites, it's only at that site and there's no fast failover of gateways or anything, then be aware that obviously if you're not on the same subnet and it needs to go to the gateway, then you may not actually get the access that you expect. So just understand what's going on at that level of the IP network connectivity. How was the race won? Well, the simplest answer is whoever gets to that quorum first. Generally a race, so the first site that gets in and locks it will be the one that wins it. So again, consider the network path that's going to happen for each of the sites. That latency may dictate who the winner is. And so because of that, there's a 50-50 chance of each site in reality winning. But if you're running in an active passive mode, you probably want the active site to carry on rather than the passive one. And that 50-50 chance, as per just as inserting a USB stick or a USB device, you've got a 50-50 chance of getting it right. More often than not, get it wrong in the first place and then find that it was actually the right way anyway. But anyway, at that point, you want to make sure that you guarantee that or at least you get a preference to the active site. So we have this preferred option. You can say, I would rather site 1 carries on. And that effectively gives it a 3-second head start in this quorum race. And then if you don't have the ability to have a quorum at all, but again, you always want one site to carry on, particularly in a split brain scenario, we have this concept of a winner site. So you can say, this site wins, doesn't matter, it will always win. Be careful with that. Obviously, if you do have genuine failures, then maybe you have to actually bring up the other site manually yourself. So how are we doing? 15 minutes, so almost there. Just to finish off a little bit on the I/O processing, some things to just understand about how HyperSwap is processing those I/Os that flow through the system, and then we'll have some time for some questions. So there is this concept of a primary and a secondary within HyperSwap. So although you have active access and that either site can read and write to a given volume, generally because most people run in that kind of active passive mode, and also because we have to ensure consistency on the right ordering. So if you have an application coming in and it sends an I/O now and then it sends an I/O now, we've got to make sure that that first one is processed first, in which case you need one of the sites to coordinate all of that. So we have a primary site whose responsibility for, on an individual volume basis, is to coordinate the right order consistency for that volume. So a write comes in on site 1, and this particular volume is set with the primary of site 1. Therefore, one can say, okay, I can process that write. I'm the primary, so it will mirror the write to the other system. Once that other system has the write and says, yes, I've got that, it will acknowledge back to the original, to the first site, and then finally we can acknowledge back to the host. So there's one round trip across the link. Obviously, we have to do that to guarantee the data is there at the other site, and then the ACK comes back and is acknowledged as per normal. So that's the write coming in to the primary. if you are running in a truly active-active scenario, it may well be that a write comes in at the secondary site. So in the same situation here, the volume is marked as primary at site 1, but we get a write in at site 2 for that volume. So here we have to do a little bit of extra processing to ensure that write order consistency. Since we are not the owner or the primary for this volume, we have to tell the primary, we want to do this write. It came in at this point in time. Please ensure the consistency of the write. So the first thing it will do is it will forward that write. Now we've always got to make a copy of the data on both sides anyway, because we've got to cache it there and write it in both places. So this operation would always happen anyway. But it is actually a forward of the data as opposed to a mirror of the data. So once it's got it, it then handles it through its consistency, and it will commit that write back. So it will send a message back to the site that it came in on. Say, yes, okay, now you can commit that write. So it will then commit it into cache, and this maintains this consistency in write order. It will then acknowledge back, yes, I've committed that write. Finally, we will acknowledge back, because obviously the write came in at site 2, so we have to complete the write at site 2 to say, yes, that's come in, it's gone across there, and then we acknowledge it back up to the host again. So there's that extra round trip that has to happen when it comes in at the secondary. So in most cases, it's going to come in at the primary. So summary of all of that there. One thing to note is if all I/O is coming in at the secondary, we assume that you've set it up wrong and that actually you wanted that to be the primary. And so in that case, we will automatically switch the primary ownership if all I/O for the last 15 minutes has come in at the wrong site or at the secondary site. So we'll try and rectify that and improve it. All of the subsequent traffic, also all those other steps I was talking about, are just messaging. So we're only sending the data once. It's just we have to keep things in lockstep and consistency. And for reads, none of that additional processing is needed. So the read I/O is handled by whichever is the receiving site, no matter what. So one final comment, and I've had a customer who did this and then said, well, you didn't tell me not to do it, so I make a point of making sure nobody else falls into this trap. Don't host the IP Quorum application on a volume on the same system that it's providing Quorum for. It may seem obvious, but at the point that that Quorum race starts, all I/O is paused. Because that application is running and is essentially on using storage from the system it's trying to protect, it cannot actually lock it. It can't make a mark. It can't write that it's locked it. And so both sites will halt at that point. This is if you didn't have a Quorum device. So just beware, don't do that. So there are 4 links there. Obviously, these will be available on for the download afterwards. You can click on specific red books on HyperSwap, one all about replication, there's one on IP replication, and then there's a new red piece as well on 3-site replication that was introduced earlier this year. And at that point, I will stop and see if we have any questions that came up during all of that haven't been answered.
I reckon that there are a few that are already that were already answered by G and Seneca, and many thanks, Seneca. Seneca was thinking that he was here only to listen to Barry, but we put him to work. That's what we do. But I reckon there was a question from Dario that was not answered. Let me just go back.
No, I think we've answered it. It was Daryl's question asking, is it therefore true that HyperSwap gives you twice the potential I/O bandwidth per volume? And I think the answer is no.
From a host perspective, in theory, yes, because you've got twice as many paths, but ultimately, if it's a write, you've got to mirror it, so you're doing it twice, so that uses half of it. If it's a read, in theory, if you share the reads across the two, then yes, you could get twice as much read bandwidth. but you're going to lose out on read caching. So the advantage of read caching by sticking to one site means that you've got more chance, particularly on sequential workloads. So in theory, you've got twice the bandwidth capability. You're doubling up on the amount of work you got to do, and you lose some potentially on cache effectiveness.
Okay, no, it's not a silly question there. And by the way, I reckon that Barry fixed the link in the box folder. The box folder, public box folder, had a problem with the expiration date, so I managed to fix it. But Box created another link, so we needed to just update the link on Barry's blog. Can I ask my question? It is more an architecture question than anything else. I was talking to a few clients and then business partner the last weeks, and we have lots of options of high availability, which, by the way, just to highlight the point, it doesn't replace backup, right? So we're talking about high availability. You still need, is highly recommended to have an air gap to protect your data from disasters, right? From outages. But they were kind of not confused, but they were kind of asking, what are the best place or the best use of enhanced stretched cluster, the new feature on the FS, and what are the best use for the HyperSwap on the flash system? We can use anyone, or what do you recommend? Well, if that's the case, that's the problem. We use one, and in another way, you use the other one.
So, two things would be scaling and kind of performance in a way. So what Ability is talking about is there is a feature that you can add on to, if you buy a flash system, you can add the enhanced high availability option onto that. And essentially what that's giving you is some SVC hardware to in front of the flash system and give you stretch cluster on top of the flash system. So you obviously need two flash systems plus the high availability nodes. At that point, you can do 3 sites. So there's the first thing that you can do. You can then do DR on top of high availability. At the moment, HyperSwap is limited to only doing HA. You can't have a third site. Although we've discussed it, we're working on that because obviously we've just introduced 3 site for normal replication. So that's one thing. If you want 3 sites, then stretch cluster or the enhanced high availability option. The other one would be to divorce all of that additional replication workload and away from the flash system and give it to the SVC to do. So you've got extra CPU and memory and cache and all those things running up at that level. And the other thing is scalability. So HyperSwap has some limits, just over 1,000 volumes in a HyperSwap solution. There's potentially some capacity limits at just over 1.5 petabytes, I think, you can have in a HyperSwap or IO group, whereas having the SVC on top doesn't have those limits. You can have 10,000 volumes, so 5,000 volumes on the SVC side, and there is no capacity limit on it. So there's a few sort of higher end. It's probably more from a larger scale customer. Maybe makes more sense to have the EHA option. And also you can obviously then put multiple storage devices behind one system as opposed to just having a single system.
You're muted, Abilio.
Sorry, that's clarified the question. So thanks for that. Any other questions that we are going to? Oh yeah, so
Daryl's just saying that the link for the downloads is still not working as of now, 4:51, and it wasn't working at 4 o'clock. So yeah, it looks like we've still got a challenge with the downloads at the moment.
If Abilio's changed the link, I need to go into the blog.
And the blog and edit it.
I will do that.
Okay, you can blame me. Yes, it's always Abilio's fault. Yeah.
If you get a new link, you can post it in the chat, Abilia.
In the chat if you've got the link to it. Yeah.
I'll do that right now. Public access, so share, copy, and done. Ta-da!
Okay, hopefully Daryl's got that one now, can see it.
Hey Derek, can you give a try on that one, please? Just to see if it is working. And is there any concern about capacity? Because, I mean, when you use enhanced, I know that that's not the topic, but when you use enhanced structured cluster on the Flash system, you're supposed to have some one or two systems in the background, right?
So you need to double up. So you obviously need one system at each site. So any of these, obviously, you're making a full copy ultimately of your data, and so you have to double up the capacity. But if it's a standard EHA or stretch cluster, it's just a doubling. If it's a HyperSwap, HyperSwap actually makes use of some change volumes for consistency as well. I kind of left that out because once you start going into that, you start getting lost in the weeds of the details. It handles all of that itself automatically, but there does need to be some small additional amount of capacity to handle those change volumes. And it's around the point where HyperSwap stops. If you have a site failure, it will change records so that it knows how much to have to synchronize back in the event of it having stopped in the first place.
Is there any risk on using those? I know that we need a link speed connection between both sides, and I remember having a client back in my home country where we put it like it was a DS8000 HyperSwap, but it was based on an IP link. It was not necessarily an IP link. It was like they say layer 2 link. So it's still IP based, but it has all those latency problems of an IP. So do you see any risk in doing this? Although technically can work, but is not a recommended practice for HA type of environment, right?
So for HyperSwap, it can be an IP link, but it must be an FC IP link. So we require it to be a fiber channel connectivity between the sites, unless you're using iSer, so the iSCSI extensions for RDMA. And that means it's a 25 gig link. So for most people, this will be FCIP routers providing the site-to-site link, or direct fiber cables. I mean, you can run this from one room to another, obviously, give you HA kind of locally, or even rack to rack, in which case you just have some long fiber cables running there. Obviously, dark fiber is the other way of doing it as well, but it does need that. And in the red book, it will tell you all about the kind of requirements on that bandwidth, just for the heartbeating as much as anything else. So even before you get started, there's a certain amount of heartbeat that has to happen over those cluster links.
Oh, awesome! Yeah, that's pretty, and that's when the business requires HA like we're presenting. Yes, we need it, and I reckon that doing a step back, you would say that okay, what are talking about requirements? What are your RPO and RTO requirements, so we can architect the best solution for it, right?
Well, and as you see from that, we have pretty much, we can go from a wet piece of string, if that's what you have as your connection between your sites, then we'd obviously recommend GlobalMirror with change volumes, versus a full fiber channel connectivity, then HA is not a problem. So we can provide anything and in between.
Awesome. Any comments, Andrew or Seneca, our new acquisition of the back to school team?
No, this is good. I was just setting a chat, just thanking everybody for coming to our sessions over the last, was it 11 weeks? I think it is. I can't remember now because we had a 2-week
journey,
break in there. And I've greatly enjoyed it. I've learned a lot, and hopefully we've taught or refreshed some of our participants over the time with their knowledge as well.
Indeed, and I think Daryl wins the award, I think, for attending every session.
Indeed. Hey Andrew, make sure that you buy a beer for Daryl for that. He needs a badge for it. That's for sure.
Yeah, I think I have to do a road trip up to the Sands or Blenheim to go take him one.
Yeah, awesome. Barry, it's your show, so you please feel free. As you are awarded as the wild duck, you can finish your comments and let's celebrate. Maybe we can do this next year sometime.
Yeah, I'll just add my thanks to everyone who's attended. Hopefully everyone's learned something from it. Echo that from Andrew. I learned a lot on the power side and on the Z side that I didn't know before. So thanks for everyone for attending.
Sweet as. Well, thanks guys. Keep safe. Kakaha. See you maybe in IBM System Back to School 2021. Let's see. Cheers. Bye.